Okay, so welcome guys to week 19. Today we're going to talk about steel frame structures, and I have a few, like 4 models. Like last time I had 4 models with different applications in it. This is a model a colleague of mine developed here inside the company. It can be like a passageway or a bridge, I don't know. It's a 3D frame structure with bracings and 2 levels, like a lower deck and an upper deck, and some vertical connections. So let's start with how we model this geometry. So let's say you can create a 3D frame steel structure in the same way that you create a 3D frame concrete structure. The only difference is that you might be interested in. We already discussed this when we talked about infill panels, that our model has trusses, so has edges in the geometry. Maybe you're interested in not joining elements at their intersection. So whenever you model them, you just have to remember to use the command make wire instead of the command merge. I would show you in one of the models, I used one of the commands and in the other one, so I can show you the differences. So this model has disjoint geometries. As you can see here in the work tree, there's a lot of geometries. We have a huge wire with the overall structure. And then to model the supports of this structure, we decided to model like 2 faces, modeling like the piles of a supposed passageway. And then we have 2 lines that could be, let's say, additional beams, or it could be the soil. It depends on how you want to model this. And then we have a series of points. Like I'm going to turn off the interaction to show you the points. So this is something that is done often to model seismic isolators, or anyway, construction joints into bridges. You can create either points or lines, it does not matter. The important one is that you create the nodes with which you can assign an interaction in between. So we created 3 different interactions, one between the piles and the 2 different nodes. This is all done to create a gap in between this structure and something else that comes afterwards, and to give a specific property to this gap. In this case, we only created rigid links, but you can assign any other kind of viscous behavior, or you can assign different kind of boundary conditions. You can put the structure in a way that it slides on one side and then it's like just pinning on the other side. So you can define what you prefer. In this case, we have 3 different interactions. One, let's say at the base level, one to which you can apply your, we define it like this because it would be how the geometry, if you imagine like a deck to be this height, maybe you can imagine the connection with the rest to be at a lower point. And then another rigid geometry, a rigid link connecting the whole structure to the assigned property. So there are 3 different interactions: this structure, 2 lines, 2 faces, and points as geometries. All of these geometries are connected with these interactions. So just for you to know that whenever you create a structure like this, you need to remember to connect everything together, either with an interaction or with a merge or make wire command. Otherwise, with this joint geometry, you will have this joint mesh and your model will be singular. Later on, we defined 2 definitions, one for the gravity analysis and one for a nonlinear time history analysis. Subsequently, there's a definition of sections. For this specific example, I just used elastic sections and elastic material properties. So we have this HE400B for all of the sections that are the bracing and the horizontal decks. And then we have all the connections in between these structures and the, let's say, lower deck, sorry, not horizontal deck. There was the upper deck, and then this is the lower deck, to come out in this kind of configuration. Then we have an elastic membrane plate section for the 2 supports, which are faces. In this case, you can assign either a density if you don't want to use the mass, or you can just apply a mass. I did both, but here it should have been like this. And then you have to assign a stiffness, a Poisson coefficient, and a thickness. In this case, our model is in meters, kilonewton meters in this case. So just to make a change to all the other kind of examples that I gave you that was in Newton millimeters. And like this, we have an elastic membrane plate section for these faces as supports. This is just the basics in which how you can use a face, so a shell or a plate element inside STKO. I know that we talked just about 3D frame structure, but just for you to be introduced to it, you can use this one and the shell as the shell cook for element. And you have to remember to assign specific mesh control. I will tell you later on. So what's next? The only thing that we added, instead of applying the rigid link condition to all of the interactions that I created, just to show you how you can do if you want to apply a different kind of stiffness to this kind of link, you can create an elastic material with a specific stiffness. In this case, for me, it's a large stiffness because I don't want the link to be viscous or to be soft. I want it to be rigid. And then you assign it to a zero length material in all of the direction in this case, that you directly assign to the interaction just by drag and dropping it as you do for assigning physical properties to faces or to edges. So this is the same in the same way. Then we define an elastic beam element for all of the edges of our structure. Shell element, as I said, for the faces, and a zero length element for this interaction. You cannot apply a physical property without applying an element property. This is always something you have to remember. Later on, the structure is fixed at the base. Rigid link multi-point constraints are applied to both of the rigid interactions of the beam type. Because as you know, the bar type does not take into account the rotational effect, the rotational degrees of freedom. Then we can define mass for both the edges and the faces, and self-weight for all. So for beams, we can always use elastic beam uniform. There's no difference in the use of elastic beam uniform or in the use of the edge force. It's the same, exactly the same. So you can use either. And here we set up a very simple analysis. It's a gravity analysis with these loads applied to it. We have to use the penalty method because we have a rigid link. And when we apply a uniform excitation in the y direction using this accelerogram that I defined here in the definition, here. And then from here, create a transient analysis, as I explained to you in the nonlinear time history analysis webinar. We give the number of increment, has the number of steps of our series, and the duration has the total duration of our series so that we don't miss any of the spots. I mean, I will run this analysis, but just for you to show that it does run, maybe outside of here, because I already have my result. And we have our gravity analysis, and then we start with the linear time history that will last a long time because it's 24,000 steps. Just for you to see what happens if you don't assign the right mesh control to the faces. For example, if I say that these two faces has to be unstructural and with a triangular topology, and I recreate my mesh, I have now a diagonal here. And when I try to build my model, I will get an error. It says the nodal spatial dimension vector obtained from the element module must have the same size as the number of nodes in the element. This is something that we never encountered before because we always used beam elements with edges and nothing more. But just for you to remember that if you apply a specific shell element to a face, the shell element has to be coherent with the mesh that you are creating. So if the shell element has 4 nodes, your mesh has to have 4 nodes. In this case, to mesh with 4 nodes, we would have to use the structure mesh and the quadrilateral element and apply it to both faces. and then recreate your mesh. Remember, you always towards recreate your mesh, otherwise it will not be updated. So this is for you to show you what's the kind of result that you obtain from this type of analysis. Sorry, it takes some time. Remember that I told you that the bracing is not connected at the base, so you will be able to see this, how this impacts the analysis in the gravity load. Of course, the structure does not move a lot under self-weight, so we'll have to increment the deformation in the post-processor to be able to see the actual result. But then if we open up here and we want to see the displacement in the vertical direction of a stage 1, and at the last step, incrementing, oops, maybe too much, you will see that in this case, at the lower deck, I decided to not connect the bracing with the horizontal element. So this is something that maybe you will need to do if you're modeling a steel structure, because sometimes connections are not continuous, they are overlapped. And this is something that maybe you don't have to model the gap that is in between the elements. You don't need to take account of that. You can model everything in the same plane, but you do need to model the disconnection. And this is a way to do it, just for you to remind you. I'm not sure everybody remembers. You do create, for example, this kind of structure. And then we would copy it here. Oops. So if here we merge, the node will appear. If here we make wire, the node does not appear. Okay. And this is good. The same goes if there are more than 2 beams going in the same nodes. Like here in this case, there's like 6. And not 4, and it's the same, it works in the same way. So this is what happens. What can you do more about steel structure that you would like to know maybe in STKO? So one thing that can be useful, I guess, I mean, I imagine, because this is what the application have been until now, is that for now, all the beams that we modeled, the bracing, the horizontal deck, there's lower and there's superior and lower deck, the vertical elements, everything is connected in a rigid way because it's merged, it's a wire. But what if you want to release some of the degrees of freedom in these nodes? How do you do it? So something that is so often done in the bracing is to release the rotational degrees of freedom and make these kind of elements behave only with a specific axial stiffness and maybe torsional one, but not a rotational one. If you know the stiffness of the joint, this is something that you can also input. I will show you with my next example. It's the same exact passageway, but it has an addition. So what I've done here is I did the same exact procedure that you do to assign a zero length element to an interaction, but instead of assigning it to an interaction, I created my zero length material with different materials in the different degrees of freedom. So in this case, I don't want anything in the rotational degrees of freedom, not in the torsional direction, but in the ones, of course, just remember that when it's dir 1, dir 2, and dir 3, and there is not like x, y, and y, it refers to the local axis of the beam. So in this case, maybe you would be, okay, but how do I do it? These elements are inclined, so how do I assign a specific direction to it? I do it because these directions refer to the local axis of the elements, just for you to see them. These are the local axis of the elements. So the x-axis is always the characteristic axis, and it's lying in the direction, let's say, in the longitudinal direction of the beam element, and the rest can be oriented differently if you want. So In this case, I created for both of these, as you can see, these are just elastic materials with different stiffnesses. I created one for the actual direction, which I want to be rigid. I want the connection to be rigid in the axial direction. So for stress and forces to be transferred. And then I have one which has a torsional stiffness. And I could add another one if I want or don't want. If I know what is the stiffness of the joint, I can use a specific stiffness to give, let's say, a softer stiffness compared to the rigid one, in this case, for the rotational degrees of freedom, or I can give none. So it depends on what you know about your structure. And how do I calculate these kind of stiffnesses? So for the rigid one, I want my largest section in the joint to provide the stiffness as much as, let's say, the stiffness of that element can yield. So I make, for the penalty method, I make this kind of calculations in which I say, okay, my stiffness is, my E is this number, then my area is this number. So E per area is a certain order of magnitude. I will increment that order of magnitude of a couple of levels. And then this way I can get a rigid connection, because the problem is in this case is that if you start adding very, very high numbers in this kind of applications, you could get singularity problems or ill conditions problems if you have too high or too low numbers. So because if the number is too low, then the connection will not happen. If the number is too high, your matrices will have too large number to invert, and it will be complicated. So just remember to do it like that. And in this case, you can do the same for the torsional stiffness. You take your G, your shear modulus, you take your J, and then you make a couple order of magnitude more than GJ that you have in your structure. And in this case, instead of applying the zero length to the node, this you cannot do. But what you can do is you can use this inch beam special purpose element, special purpose physical property, and then you need also the inch beam special purpose element, and assign a section for your overall beam, and then specific zero length material, as we defined before, the same one for the top and the end node. The only difference between this model and the one before is that we need to add, you cannot just apply this physical property and then keep the elastic beam column. Otherwise, your model will not run. You will need to apply a specific inch beam element referencing another in the same case. So you will have to have created the elastic beam column or force beam column, displacement beam column, whatever, and also a zero length element. We already had these because we applied that to the interaction. So we were lucky. Like this, we have the possibility to, let's say, simulate the absence of connections in terms of rotation. I can show you the result. I ran the same exact analysis here. It's a bit long because the nonlinear time history was quite long. I will show you also the result of that just for the sake of illustrating it. Sometimes it's just fun to play around with the models and see them shake. And then after this, I will show you two different applications in which I applied a very strong action in one direction, just to show you what's the difference between the use of a co-rotational geometric nonlinearity and a linear geometric linearity. Because that's something that we often use in steel structure that we want to see. We want to study large displacement problems, and that can be done by just applying the geometric nonlinearities, and you can already see a very big difference in the results. Of course, only if you have very, very large forces. So this takes a while. Have you guys have ever modeled already steel structure, or are interested in modeling any steel structure with STKO and OpenSeas? Not many people. Okay, well, I mean, this was done also to be kind of comprehensive with our series so that we can cover a bit all of the topics. So this is our second structure. Let me show you displacement. If I go at the end of my series with this one, and then at the end of my series with this one, you see just I already have a different result. I mean, of course, whoop. This was the result of my transient analysis. I was applying this acceleration and my structure was moving. Of course, I did not apply very large acceleration, so I'm not moving more than 10 centimeters, which is already a lot, but still. So how I can check that I did something different in these two models? Something that you can ask for in the recorder to check this is the local forces, because we're using beams, so local forces can give us information at the extremity of the elements, and we can see what is actually happening at the extremity. So for example, if I want to see the moment, let me just put it a bit smaller. Let's move at the beginning of the analysis, just in the first, maybe at the 10th step, when I'm actually just applying my self-weight. And let me just show you the bracings. Just the ones on this side, they are the same. So as you can see, in this case, this is my second model, the one in which I added this, the zero length element, and I gave freedom in the rotational. I have zero moment. This moment is like e to the power of minus 10 to the power of minus 15, so it's almost zero. This is just a numerical error. But then if I go in my other structure, I move again to the beginning, like step 10. I just turn on my bracing in one direction. I'm going to go and see my moment and then change to my first analysis. You can see that I still have a lot of moment transferring from these elements to the horizontal upper deck and lower deck. So this is something that you would maybe want to use, and it can be very useful to model differences in the way steel elements connect to each other. And the result is much different. So you can see that I have a completely different result. And I also can have, let's go back to our, yep, I want to go to stage 1. At the end, this is my displacement magnitude. And then if I go to stage 1, at the end, this is my displacement magnitude. So in terms of displacement magnitude, vertical displacement magnitude, it does not give me so much of a difference. But in terms of moment, I have a very large difference in between what's happening on the bracing. And it can also give a big difference in what's happening in the rest of the structure. So just for you to know how to do it, remember to use both the hinge beam as a physical property and the hinge beam as an element properties. Whoops, sorry. So moving forward, I will just show you very quickly. I will start with this one because it's just, the two models are the same. I just changed, I went here and I changed the transformation type, the geometric transformation type. We had another webinar on another class on geometric nonlinearities. So I just changed the transformation type in between these two models, model 36 and 37. And I applied a very strong force at the center, pushing down the structure. There's no nonlinear time history here. So if I create a new post-processor document and just load these two results, and instead of comparing them in two different plot groups, I will try to do it in the same plot group now. 36, 37. I want to see displacement. Just for you to know, sometimes it's always displacement here has appeared. In the post-processor, the results are organized alphabetically. So you will always see the first in terms of alphabetical order. And then I have displacement and displacement. So I don't know if you guys know which is which, but I'd like you to guess. So which one is the one with the rotational geometric transformation and which one is the one with the linear geometric transformation? What do you think? I'm gonna ask any questions. So this is just like to chat. It's not to check anything. I also had to think about it a bit. What do you think, Larry?
The linear one is the one with less deformation?
Exactly the opposite. This is because, yes, so what's happening here is that axial forces are developing inside of the rotational formulation. And so I don't have the same geometric effect. This is because I can study with the geometric transformation, I can study the contribution of the geometric nonlinearity, but it does not mean that I will have large displacement, even if it's used with large displacement problems. So the difference is actually that I can reach larger displacement exactly because I use this kind of geometric transformation that takes into account how my structure geometrically works. Let's see if we can see this difference. I did not try beforehand in terms of axial forces. I know I did not ask for these results, so I would have to rerun the analysis, but it's very fast. So let's do it. Local force. And then I do it with the other model. I go here and I ask for local force. Yep. So let's reload. Now I do have local forces. I want to see. How come I cannot see it? Here they are. So let's make them small. But I'm not sure I'm seeing both. So here I have the second example. Let's reload the first example too. Yeah, I also have the other example now. You can see that this is much different. But probably it's better to do in two different plot groups this time because I want to see the values and I want to see which is which. So I put this a bit smaller. So let's see. Example 37 is the one with the rotational, and this is the axial force that we have in the central elements. And let's see, in the central elements here, at the end of the analysis of the second step, we have the same amount. Let me see. Sure. Yeah, we do have the same amount. Let's see about displacement 1. Displacement 1. Okay. Let's see if we can see any differences in between these two in terms of axial forces. Not so much. Ah, yes, because it's the same recorder. Okay, but still not so much. Yeah, but it did change a little. So let me move you guys on the side. Whoop. Okay, so here we have the first example with the elastic transformation. And here we have the second example with the elastic transformation. As you can see, there is less axial force that has been developing on the vertical elements in the first example, or more. Yes, there is more. And there is this one, 2.36 is much higher. Yep, is much higher than this one, also almost double. So let's say the geometric configuration of this structure is actually pulling the structure up. It's not allowing it to deform as much as if it was completely elastic in terms of geometrical effects. Just for you to see, as you can see here, I merged all the elements at the base deck. So we have a different response that we had before with the unmerged and only made wire elements. So that's all for steel structure. There's not much more that you can do in terms of frame elements. You could explore a lot in terms of micro modeling or detail modeling of nodes by modeling directly like how junctions are created with bolts and other elements. And that can be done also in the same way that rebar are embedded into solids. So with partially solid elements, partially beams, beam to solid coupling connections. So there's a lot of things that can be explored, but for now, as it goes for 3D frame structure, what you have to remember is how to model bracings, how to release some of the degrees of freedom at the ends of the bracing, how to merge them or made wire. And if you want to use co-rotational transformation to capture nonlinear effects and also to see, I mean, this is really easy and it's something that I think it's mostly done with steel structures, because if you think about it, those are the ones that can sustain very large displacement. And also those are the ones that I do not really need to use nonlinear analysis in terms of material, because I more or less know what's the limit of my material. And I do not want to see cracking or any other kind of phenomenon that can develop to overstress, can be seen like in terms of stress results. So I want to see just a linear material, but nonlinear geometrical transformation. So I don't know if you guys have any questions. I know maybe this topic did not interest you much. There was someone who asked for it at the beginning. Hi Hernan, welcome. Or maybe it was
Hi,
just...
thank you. Hi to everyone.
Okay. So if you guys have any questions or also have any requests for explanation on other topics, we have a lot of time today, so we can also use it for other things if steel structures don't really matter to you.
I have a question. I know I know the difference between the merge and the wire, but as you showed in the first example, you did the wire, so in the lower deck, the cross is the one that is released, and the transversal beam stays up. How can you make it like, how do you give the hierarchy
there?
Sorry?
It's just because of the load, because there was more load on the diagonal elements, and the diagonal elements are longer, so they would inflect more. I don't know if you say inflect in English.
No, but the thing is, it looks like, or this is what I understood, like the transversal one, because you did the wiring thing, so the center is not the point, so they are disconnected.
Yeah,
right?
But they are on the same plane.
They are, so I cannot make a hierarchy. Like if I draw the first ones first and then the last one on top, I make that one on top.
You can do is to, let me show you, but you would have to create different sections. And in this case, we have the same sections. But let's say that I have a different section here. And I know my section is, let's see how tall it is. 2 understand, and I wanted to push it up. So I do plus, sorry, not here, but
okay,
here.
with the offset, I can make this hierarchy, right?
Yes, but in a sense, it can also end up that it goes in the same way in terms of results. And this is because you do not, I mean, in this case, this does not matter because this is the case in which everything is joint, but It depends on how much weight you put on it. Because in the end, I mean, the hierarchy is just a visualization. It's not something that you can assign and you say, okay, they will be like this. And then when they touch, there's one on top pushes the one on the bottom. This is something very refined that you do not do with the frame structure. Like, for example, if I want, I can push it a bit even more up. And I say, okay, they are like this. But this will just take into account in the difference in height in terms of element forces inside of this element, that there will be this gap, and it will any axial force will be eccentric, no? But this will not take into account what you want, no? That one, I don't know if this is what you want, but that one element touches the other element, they got down.
No, I was when I saw it, I was thinking like maybe you did something in a certain order so to obtain that result. This was my question. Like, I was not sure if this is just because of the self weight, or it's because you did something to get that result.
It was just because of the self weight.
Okay, great. That is my question. Thank you.
Welcome. Thank you for your question. So, guys, if you want also to show your models or just to ask something from previous webinar that were not clear, Valentina made a crash course this 2 weeks, so maybe she has questions or she found some errors in our files. Please do share. We only have another, go for it, yes.
Okay, I can show my model. I didn't find any mistakes in yours because I'm really beginner. But if no one has any question and I can use time, I would like.
Go, show it.
Okay.
I will have to give you permission to show.
I think I can.
Okay.
Okay. This is my model that doesn't want to run.
Okay.
I have this error, non-type object has no attribute elements. I was trying to search in forum, what does it mean? And I was thinking that some physical element properties don't assign right, but I reassigned everything and I didn't find what is wrong.
Can I request remote control? Request.
Okay, approve.
Okay. So let me see, you have...
I'm working in 2D.
Okay.
So
let's move this. Okay. So you have, let me see your geometry. You have 2 merged faces and 1 frame. What is the frame?
We need to about visualizing. It's not choosing.
Yeah, of course. Don't worry. So, okay, this is like this. Let's turn off these ones. Okay. So the first thing I see is that you have faces that are going in different directions. You see that they have different colors, no?
Yes, I remember it's from the lesson.
Did you do it on purpose or not?
No, I did it while I was doing mirroring. Yes.
Okay. So what you can do, you want everything with the zeta axis towards yourself, no? So you do like this, you select all. Like this for sure, some errors that you will encounter, you will not have. But which is this frame?
We need to select that vertex edges and the points in.
Okay, this is the frame. Yeah. It was hidden. Okay, sorry, I didn't understand. So you have like infill frame, and then contact in between, right?
Yes.
And then this one.
Fixed rotation, I'm not sure that I need. It's about application of horizontal load, but in the end, I applied my horizontal load on the beam on the left.
Then so, this you do not need. Let's make a copy of this so that you have.
It's already copied to find
good.
So
you can delete. I can butcher it then. Okay, let's take this away. What about this contact?
Okay.
Interactions, you made an interaction in between the frame and the beam in this way, and then in the frame,
left column.
The panels in this way, and then in between top, okay. Because you want to give different contact properties in different directions.
I want to, maybe it could be one. I want to consider friction in this case. I'm not sure if I will have different parameters all the same yet.
And you have for sure different kind of contact for the vertical contact. Okay, is this gap physical or is it just a gap that there's a beam here, right?
Yes, it's physical, it's because of thickness of the beam.
Okay. Then you apply the plane stress material with this thermoelasticity and another material for your mortar. Okay. Then you have concrete steel, rectangular fiber section, and into.
I use this model because I want to consider also shear in column additionally.
Okay, but like right now this tool is still under development.
Yeah.
So I don't know if Massimo or Professor Kamada, they already told you something about it?
No, I found it by myself because in a video, in tutorial, I saw different way, like if you also how you explained before when we use separately aggregator, if I call it correctly. But then I found this tool and I thought, oh, it's cool, I can do it.
It's very cool, but still it doesn't work. It works under some just specific conditions. So I would suggest, that's why it doesn't work. It doesn't, like why your model does not run. So I would suggest that you use the aggregator and you probably will put shear in both directions for the column. You want to put the shear just in the column or also in the...
I did only for column for now and only for Y direction as I'm working in 2D.
Okay,
right.
You're right. Okay, perfect. So this we have aggregator. And
I wanted also to try that new tool because there also is possibility to use different sections, for example, because I was thinking in case if I will have more steel and I want to use different section more close to joint, so it's good.
Of course. Yeah, but the tool will be ready soon. So you will be able to use it and we'll probably make a webinar to explain how it works. But for now, I would suggest you use the older tools that we have.
Okay.
And of course, if you need more sections, you can always, even if you're just like what you are doing is just using a force spin column element and a property that is like distributed in the sense that there is just a distributed plasticity. If you in this case, for example, here you say, okay, I want just 3 integration points instead of 5. I can make my element smaller and assign a different section to it.
Okay, good.
The only thing you cannot do that I think that the tool gives you the possibility is to define the distance of the integration point. No, you can arrange it and then define the section in between 2 specific points that you want. But I mean, if you have more points, unless you have very, very tiny elements, you will not have a problem. To just have more points, you will have more results. Maybe your model will be a bit heavier, but if you, as I said, you can just lower the integration point number. 3 is the minimum that you need to use. So for your beam, we just use the beam section.
Without considering shear.
no shear. Then you have quadrilateral elements.
For masonry.
Right. Then you have your contact element for your interactions. For now, it's the same everywhere. Okay. And then you have first beam column elements here. Perfect.
Mm-hmm.
So you fix the base.
Mm-hmm.
I didn't look, but I think you will click on everything, right?
Yeah, these are like no in X, no in Y.
Okay. Did we give here the options? No, we don't need to. Okay. Vertical load on the beam in the global Y direction. Load on the columns. It's a nodal load. Okay.
Mm-hmm.
So this you wanted to fix the rotation at the top, right?
Yeah, but I'm not sure that do I need to use it in my model or not, because in that tutorial, Massimo applied in a point on the top of masonry, and so he fixed a rotation and he applied to one node on the left. In my case, I applied my horizontal load to the beam, so I'm like a little bit confusing. Do I need to fix?
You can also do like this, no? To fix the rotation on the top. You can use a fixed, so if you want, you can use a fixed rotation like this. You don't, the equal depth, you need to, like if you, like, I think in the model of Massimo, maybe he had two geometries, and in the top he had an interaction, and then he applied the equal depth to the interaction, but the interaction was needed because the two geometries needed to be connected. There was something rigid to which the load was being applied. Most probably like shear. I don't remember the example.
It was masonry between two steel. He had steel beam on the top and steel beam on the bottom.
The two elements in the same way, so I didn't want to connect them. So create interaction to apply a specific equal depth, in this case in rotation. But like this, in your case, you don't have an additional rigid element to connect. You can just apply a fixity there.
Okay, I will think about it, because how they did experimentally, they applied load, vertical load to masonry through the metallic beam. So it's also can be considered as we prevent rotation, but I will think about it anyway.
But maybe you can model the metallic beam and then attach your infield panel to that beam with an equal depth like you did before. Then if you don't have an extra geometry, that interaction is just, I don't know what it's connecting what with what, you know? I don't know, what did you put as master and what did you put as slaves?
I put as master the left node, the first one would say, and all others I put as a slave one. So it was idea if, for example, we applied horizontal load just to one node on the left, all nodes will react
the same.
Yes, the same, yes. But in my case, as I apply load differently,
I don't know, you would have to create a lot of them, because then this is a master, this is a slave, this is a master, this is a slave, this is a master. Like you would have to create an interaction for each of this couple.
Sorry, no, I didn't get. No, only one node was the master, the left one, and all others.
Okay, clear. Okay, so yeah, that's also something you can do, but given that maybe the elements, then they are very far, I would suggest that you model the beam if you want.
Okay.
You can try when it runs. You can retry with your.
Francesca, if I may.
Yes, of course.
I suggest you, Valentina, to check. There is a course that Massimo imparted. I think you can find it. Not in the in the webinars, but in the one that is lectures or
e-learning.
Yeah, exactly. There is a course that Massimo did in Portugal, I think, where he explains another way of doing it that for me was better than with the slave and the masters.
Yeah, that's not in the e-learning. It's in the university courses part.
There.
Yes.
It's in the course.
That it did in Porto, I think.
Yeah.
Okay, because e-learning, I watched everything. I think I can confuse something, but I
no, it's not in.
For 2 weeks, I studied everything.
If you go to university courses, exactly, university courses, Francesca was right, and you go to the course of the 20th of April, there is one that is called RC shear wall. And then there is one that is in plane analysis of masonry walls, micro and macro modeling. There he explains the other way of doing it. So it's not using the master and a slave, but using an imposed displacement. So and for me, because I'm modeling something similar to this, this way was better.
Sorry, can I ask one more time? It was RS shear wall, and it's two different lessons.
Two different, yes. It's day one, online course, day one, and it's the last one. In plane analysis of masonry walls, micro and macro modeling. It's a university.
Thank you a lot, Larissa, because it's a lot of information, and it's difficult also to find what is more useful. Thank you.
So here you missed out on some cuts.
I see.
And that's why it's giving you a triangular mesh in some places. Decides to, I mean, it wouldn't have to, but it just decides to create triangles instead of squares. So I think now if we run it, it will give us a different error. I hope that we fix the first one, at least, and then we just don't, can I run it here?
Yes.
Oops, no, it gives a different error. It gives the same error, sorry.
The same,
On faces though, on faces. Maybe this is not the right way to use this one. What do you think, Larissa? That you create a plane stress and you just select the domoticity 3D.
It was exactly as Massimo did in his webinar. I don't think.
Yeah. To make it to put a 3D material in a 2D model. Yes. This was also one of the errors I have when I changed to 3D, but I keep on doing this.
Okay. So maybe if you do this, maybe the error is given by the fact, but it should be a different error. It should be telling you that you have an element with different amount of nodes compared to the one to the mesh elements that you provide. So in this case, it still tells you that you have a wrong physical property applied. Let's see, select all the bricks. Did you select with the...
I checked 20 times about that I assigned correctly physical and element properties, because I was thinking that it's the main mistake. So I did from this window, from another selection, I don't think that problem in selection. Maybe I did with contact something wrong, because for me the most difficult part, it was contact. I use the last contact.
Yeah, but maybe you have to create an element for it too, no? Let's see.
I was also thinking, but I checked examples that Massimo showed his last tutorial on last week, when he presented this new contact element, and without physical properties, it works in his case.
So, because I've never used this contact element yet, so I don't know.
Yeah, it's a new one.
Okay, but you did apply it everywhere. Select, they are not shown.
I know that they're a little bit about also what we consider master node, what we consider slave when we do contact from also direction and local axis, but I think it can influence on result, but it shouldn't influence that he doesn't want to run it at all. Like I'm not completely sure that I did contact properly from about local axis.
Let me check it. I have another model. Wait, can I exit this? No, exit full screen. Yeah, I'll check on my computer. I have another model in which I did contact, even if it's not with the same element, just to see if I use the same kind of setup. And if anybody else wants to pitch in and to check what's wrong with Valentina models, this is what we wanted actually this course to be, like everybody solving a problem together. So you are welcome to join. Or at some point we call Massimo, which is also an option. Now, in the meantime, maybe you can fix those.
I will stop sharing.
If you want to do it.
Okay. Thank you. I will fix meantime.
Okay. Beam shear. Okay, let's just try and go by attempts. I don't know if you've done already, but let's just share again and see maybe the graphic material for the bricks. Let's see if that works. And maybe then it's that application. Otherwise, it's something else.
Okay. I share back.
So like, for example, here, we can just, I don't know, what unit are you modeling?
Millimeter Newton.
Okay. Let's see if we, do you have a selection set with this stuff?
No, I didn't do, because my model is so small. I didn't find a way what to do in selection set.
Yeah, but for example, right now we can keep the brick and the mortar selection so that we don't lose it if we want to reapply. Okay, let's try. We have to erase this. Of course, when you build, you have to recreate the interaction. But how come these nodes are also selected with the contact?
Mm-hmm.
Like, why is not just the bottom nodes?
Mm-hmm. I think it's a mistake. It's about selection because it was difficult to select.
Okay, so maybe next time you can first select, then create the selection set, and with the selection set, create the interaction.
Mm-hmm.
Let's see if now it gives us the same error. Yes. Untitled objects W elements. All faces. Okay. Let's see. I called Massimo, but he is in a meeting. So
it's okay. I can try more. I was just spending 2 days to try to find a mistake, and I was thinking maybe it's so easy.
I don't know, maybe it is, but we don't see it. That's also an option, huh?
Is it my first model, maybe?
Yeah, it's maybe it is, and we don't see it. Yeah, it's important that these kind of elements are not applied to nodes, for example. I don't know. No, that's not the case. I don't think it's the case. Well, yeah, you can try again a bit more, and then you can post it on the forum, and whenever we have time, we can check it for you. Okay.
Okay. Thank you very much. I will fix at least that small mistakes that we found that it looks better. Thank you.
Hi, Francesca.
Do you have a question? Hello? Hi, can you hear me?
Yes, of course. Hello, everyone. I am from Peru. I study about RC frame with masonry infill, and I have the same problem that Valentin.
Mm-hmm.
And I need to compare RC frames concrete with
Spanish, and we ask Larissa to translate.
Okay. Sorry. Tengo el mismo problema que Valentina porque estoy haciendo una comparación entre pórticos de concreto sin albañilería.
Relleno y con relleno.
Sí, exacto. Porque necesito básicamente ver los problemas del concreto, ya sea con columna corta. Perdón, claro, con lo que genera la albañilería con columna corta.
Okay.
Entonces, he intentado hacer el mismo modelo que Valentina, pero también he visto que tengo los mismos problemas.
¿Pero también con contacto?
Yes, sí. No es confinado, es solo con contacto.
So he's doing exactly the same. So he has a frame, and he's studying a frame with the infill and a frame without the infill. And he has the same problem. He's doing it with contact.
But you said it's not confined?
It's not confined. No está confinado.
But if how can it be not how do you do the contact if it's not confined? Just on the bottom. Contact on the bottom?
¿Cómo tenés hecho las boundary conditions?
Only with zero length contact.
Sí, if it's not confined,
language problem.
Confined on the bottom, so it's just up, like it's just standing on a beam, but it's not. There's no columns on the sides. This is what you're saying.
No. He has the columns. Tenés las columnas así como el marco.
Yes.
Tenés las columnas y adentro tenés el infill. ¿Y el problema de contacto dónde lo tenés?
En las esquinas, justamente.
O sea, el contacto entre cómo se mueve el marco en la esquina con el relleno.
Así, afirmativo.
Okay, so the thing is, he has the frame, so in the corner with of the reinforced frame and the masonry, he has there a contact element, so they move together, and here he's having a problem. He has a 0 contact length element there, and he's having a problem with that.
Okay, but do you have the same error, non-type object applied to an element? The same exact error or another error?
Yes, how to apply the contact element.
Claro, no, ella está preguntando si tenés el error que tenés es el mismo que tenía recién Valentina, el non-type element.
Sí, exacto.
¿O es otro error?
No, tengo un mismo mensaje.
Okay, we didn't solve it. So maybe you can also post on the forum, and if you want to write in Spanish, to write in Spanish, there's no problem. The Massimo speaks Spanish, and then we can try to solve it there, because I don't know. I mean, contact applications are out of the scope of these webinars, but we can try and help you for sure. I mean, will help you for sure, and I can also have a look of your model, like I did with Valentina here, but I can do it just tomorrow morning. Yes, Hannah just posted the forum link if you don't have it, and if you've never posted, you can just create a profile and post it there. Did you watch the latest webinar on contact, the one of last week, Edgar?
Sí pude estar presente. Y sí.
So if you just like post your model, even if it's complete, just I want to know how to create the contact here, we can help you.
Ok, sí, estoy en el trabajo, entonces voy a poner mi modelo en el foro para hacer las consultas respectivas.
Perfect. Okay. Anybody else? I've seen some people coming in late. One already left. Maybe it was put off by the Spanish.
I like how it sounds. I don't know.
Yeah, Spanish is really nice. Where are you from, Valentina?
I'm from Russia, but for now I'm a student from Turin, from Politecnico di Torino.
So the only person I don't know is Manu Lalburnwall. I don't know if you have any questions. You can also keep your mic off, no problem. I think for the rest, we went through a few things. Okay, so guys, I'll see you back next week for our last class. It's on masonry applications.
Yay.
Yes. Okay, I have to study. And thank you all for participating today, for the questions, even if we didn't solve all the problems, but we will. We always do. So just keep on watching the videos and suggesting them to your peers, to other PhD students who are learning. And then I'll see you back next week. Okay?
Okay, thank you. Thank you a lot, Francesca.
Thank you, Francesca.
Thank you all for participating. Have a good evening or morning.
Thank you. Thank you, Francesca.
Bye, Hernan.
Thank you. Yes.
Thank you. Bye-bye.
Bye.
Bye.